110 shots. And last time we were talking about the difference between what is the perceived percentage that we're supposed to make, the prediction, and what actually happens, right? But last time, where was our line?
80%. 60%.
So 80% is always our theoretical, like it's supposed to be 80%. But last time, Madison pointed out something very important. She said, but wait, the line's not going to 80%, it's going to, what was it? Where's this line going?
Like 55.
So what's the difference?
They're getting a little worse.
It's worse. This gal's got worse. She's getting tired. So then we kind of hopped over and we were talking about these bottom two questions, right? And the bottom two questions were, how could you make your guess more accurate? Like if I just let this simulation run and run and run and run and run and run and run, do you think it's going to drop down to 30?
No.
Do you think it's going to go up to 80?
No.
What do you think is going to tend to happen here?
It's going to even out.
It's going to kind of even out. If I had just given you this piece right here, what would your guess have been?
It's like 40.
You don't know.
40, 50? What if I would have given you just this?
45.
45? So the law of large numbers, which is what we're going to talk about, helps us to narrow down what is our true proportion. Okay, what is our true proportion? And the phrase that I want you to get familiar with, and the phrase that I want you to really hone in on, is this. Hold on, I got to pull up. You ever had that thing where you open up your computer and everything has been shut down, and all of a sudden you're like, I was relying on things to be open, and then they weren't? I'm a tabaholic. I got more tabs than I know what to do with. So here we go. Underneath number 5, here's what I want you to write. This is what we had from last time. Let's use that 60% here. Because last time it was trending towards 60%. Here it's trending toward like 55, right? So whether you put 55 or 60, this is the part that I want to focus on right now. Interpreting this probability. If Mrs. Gallus takes many free throws, about 60% will be made. Okay? If Mrs. Gallus takes many free throws, about 60% will be made. Honestly, guys, there's tons of ways to illustrate this. If I start flipping a coin and I have 10 trials, is it likely that I'm going to have 5 heads, 5 tails? Is it likely? Don't give me a number of how likely. But is it likely?
No.
Okay. So what if I had 7 and 3? Does that mean that there's a 70% chance of getting heads? No, it just so happens that that's what happened, right? What if I flipped it 10,000 times? What do you think the trend is going to look like? Do you think it's going to look like 7,000, 3,000? Or do you think it's going to be closer to 5,000, 5,000? What if I flip it 10 million times? Do you think it's going to look closer to 5 million and 5 million? So the law of large numbers is what we're dealing with up here. So the law of large numbers says that our empirical probability, meaning what actually happens in our trials, is going to get closer to our theoretical probability with greater numbers of trials. What does that mean? Well, it means that if I flip a coin twice, it's not a good indication if I don't get 1 heads, 1 tails. But if I flip it 2 million times, I should be getting closer and closer and closer. So let's fill in our box here with a couple notes. The first heading is going to be probability. Let's define probability here. Probability is long-run frequency. Probability is long-run frequency. It's going to be a number between 0 and 1. 0 means it cannot happen. 1 means it always happens. What's the chance that there's rain today? 60% chance of rain. What's the chance there's weather today? 100% chance. Okay? Here's two keys. In the short term, it is unpredictable. Casinos cash in on this. Oh, one more roll. I'm going to get a 6 because I haven't had a 6 in a long time. It's going to happen. It's going to happen right now. Is that true? No, because that's short term, right? But long term, it's predictable. But you got to have those many, many trials. And that's where our next little piece comes in. It's the law of large numbers. If we do something many, many times, the actual proportion will approach its probability. So the actual proportion will approach its probability. Probability is the theory. Another way to say this is the empirical probability will approach the theoretical probability. So the empirical is what is actually happening as I do these trials, as I record the coin flips, as I record the shots of the free throws. The empirical probability will approach the theoretical probability. I want you to take about 5 minutes in your groups. I'm sorry I haven't put you in new groups yet, but take about 5 minutes in your groups to go through this. Oh, check your understanding. For the first one, here's a hint. You should use a phrase like this or like from number 5 above. Okay, that's the hint for number 1. So take about 5 minutes in your groups to discuss this, and then we'll come back together.
So, if he goes hypothetical,
Ready to chat here? So here are a couple key phrases. When I give these things to you, it's to help you understand like how you might answer a question like this on the AP test, of course, but in general to understand probability. If this happens, so 55% probability that the light will be red. That is not empirical. That is the theoretical. So in theory, it's 55%. So if he approaches 100 times, is it going to be red 55% of the 55 of the times? No. Does that change? So constantly, I would get mad about this in college until I took a course on probability. Oh, it's raining. It only said there was a 40% chance of rain today. How is this possible? There's obviously a 100% chance of rain because it's raining.
Empirical versus.
Well, then I felt stupid because I understood empirical probability. Yeah, it's raining right now, but that doesn't mean that the chance of rain changed. Because he approaches and the light is red the first 3 times, it does. Every time I approach this light, it is always red. Well, that's not true. It's true in the short term because the short term is unpredictable, right? So many, many times, about 55% of the time, the light will be red. The part that I had with issue with your answer where I said be careful was about 55% of the time he will stop at the red light.
She might
You
not
see?
stop.
He might not stop. Now he probably does, right? But we need to be careful about the context here and say the probability is the context of the probability is that the light will be red. Okay. Next part. Probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. Explain your answers to your neighbor. So check it out. Probability is a measure between 0 and 1. So if the outcome is impossible, it can never occur. That will be 0. Right? So for A, that's our 0 answer. The outcome is certain. It will occur on every time of the trial. 100%. This outcome is very unlikely, but it will occur every once in a while in a long sequence of trials. Okay. This outcome will occur more often than not. Both of those. I didn't specifically say, hey, there can be more than one answer. But yeah, so these two probabilities mean more often than not. So 50-50 would be equally often. 60 would be more often than not. 99 is also more often than not. It's just way more often than not. 99 times more often than not, right? So what are your thoughts on this last one? We all sort of had a laugh about that, right? 7 girls in a row. Holy cow. Yes.
So 0.3 wouldn't be C because it says very unlikely.
Yeah, why are you
Yeah, very unlikely is the key there. Okay, what about this last one? A husband and wife decide to have children until they have at least 1 child of each sex. The couple has had 7 girls in a row. Their doctor assures them that they are much more likely to have a boy next. Explain why this doctor is wrong.
Each trial is unique.
Each
No, each.
That's a pure answer.
No, each
Are you
trial.
allowed to give like
The chance is the same for each.
Because I feel okay, I think the doctor is wrong because biologically speaking, the gender is determined by the chromosome/genetics of the father.
I don't know that.
Probability cannot be used to try to predict the gender of another child. Is that wrong? Because I used outside information.
So this is an example from the book. I actually have very mixed feelings on this for 3 reasons. One is the reason that you put forth, right? It has to do with genetics. So it's not random.
Yeah.
It is based on probability of specific genes. Number 2, using previous trials of a couple having children is a decent predictor of a probability of a subsequent child, meaning based on the gender of a specific child before, you can sort of say like you're more likely to have a boy if you've had boys or whatever. But in the short term, we can explain this purely probability-wise. Let's say even if it was a 50% chance, so take everything out of it. Take this for face value. Take it as it could be a boy or a girl. Is he still wrong? Why? What if this wasn't about babies? What if this was about coin flips? 7 heads in a row. Are you even guaranteed to have a tails the next time? No. So any event that is framed as 50% probability, you should say something like this. Probability is unpredictable in the short term.
Use like
So it's a zero.
Okay, the probability is still 50%, the chance is still 50-50. Yes?
What's how short is the short term?
How short is the short term? Is it 100? Is it 1,000? It's a good question. It's not specified.
Like roughly, would you say?
I can't.
So
I can't say
would
roughly.
you consider the dice game a short term?
Dice game. Say this. Explain that to me.
It's like because it's probability and it's short term, right? Because
Like I said, this is like casinos thrive, right? So in theory, if a person sits there and bets or keeps track of all the numbers, right? At what point would they feel 100% comfortable saying, so let's say you're playing a game where you have to predict the die roll, right? And you've watched this game being played 16,000 times, 16,000 rolls of the die. And let's just say it is crazy uncanny and everything is equal. Well, no, hold on. 15,999 times you've watched this die get rolled. And it is crazy uncanny. They are exactly equal, all 6 of them, all 5 of them, and one of them is one short. On the 16,000th roll, are you guaranteed to get that one? Even if the other 15,999 fell equal, one less. Is the 16,000th roll guaranteed?
no.
Okay, what about the 16 millionth roll? Because, it's crazy. Equal. And there's one short in this category. Are you guaranteed?
No.
So, to answer the question, what big is big enough? Okay? It takes the hope out of it, but that's why we look at the trends, and that's why we're going to talk about independence of trials. Like, a die roll is an independent event. It doesn't depend on previous events. Okay, so they're independent events. So I have no assurance that because everything has fallen equally up to this point, I make it 5 trials. I roll a 1, then a 3, then a 2, then a 4, then a 5. Oh, the next one must be a 6 because it's equally likely. No, it's an independent event, so it could just as easily be any of them. That's why we use theory to predict, but theory can't tell us empirically what's going to happen.
So is there really no strategy to a dice game?
yeah. That's a no.
I mean,
Why do you think casinos are so wealthy?
People try to predict.
Because they design games that you can't win. You can't win them consistently.
You can't predict.
People
And they
win,
watch you
but you
play
can't
poker and
predict.
then trade out
Right.
Probability is still 1/6 every time.
All right, speaking of, flip the page. Speaking of the dice game, flip the page. So Pepsi ran this promo contest on the 20-ounce bottles of soda. Some caps said, please try again, while others say you're a winner. Pepsi advertised the promotion with the slogan, 1 in 6 wins a prize. Mrs. Gallis' statistics class wonders if the company's claim is true. To find out, all 30 students in the class go to the store. Each one buys a 20-ounce bottle of the soda. 2 of the 30 students' caps say you're a winner. How many winners would you have expected to get out of the class of 30?
Five.
Why 5? Write that down. 5. Because 1/6 of 30 is 5.
So that's the theoretical.
Yes.
But you
That is the
expect.
That is
It's not
theoretical.
guaranteed.
Is it guaranteed?
No.
It is not guaranteed.
Because short term is unpredictable. Or like probability.
Short term is unpredictable. So, does this give convincing evidence that the company's 1 in 6 claim is inaccurate? Oh, I am incensed. We bought 30, only 2 of them. This is 1/15. I'm calling the company. This is unfair. So we're going to perform a simulation, and this is what we do in statistics. You perform a simulation to say, is this company's claim true? This is what we're going to spend the entire second semester doing, is designing experiments that test claims. Okay, so the claim is that it's 1 in 6. So we will assume that Pepsi is telling the truth. So what does that mean? What is our theoretical probability in our mind if we're assuming that their claim is true? 1/6. So we are assuming that if you take every bottle ever produced, that's in this promo, 1/6 of them contain winning caps. If they're telling the truth, what's the probability of getting 2 or fewer winners in a class of 30 purely by chance? Let's find out. So we need a way to predict 1 out of 6. What do you think? A die. Here we go. How unlikely? Here you go. Coming at you. All right. So here's what we're going to do. So fill in the blank. So for number 2, we could use a die. So here's what you're going to do. You need to assign the outcome, meaning you need to, ahead of time, like we talked about last chapter, right? Assign a winner, because you can't just roll a die and go, oh, it's a 3, winner! And the person's like, wait a minute, what was the winner beforehand? You're like, winner, right? So pick for yourself. Which number is going to be the winner?
3.
Write it down. Write it down right now. This is your assignment.
Does it have to be even number of winners and losers? So like 3 numbers of winners and 3 numbers?
Should it be even numbers of winners and losers for our simulation?
Oh, it'd be
No,
1 and
because
6 and 2.
we are trying to model this contest. So 1 and 6 wins. So you assign one number as the winner, and you need to say the others are. Now be gentle. But yeah, they're losers, right? So for me, I said 1 is the winner, 2 through 6 are losers. For you, it could say 3 is the winner, 1, 2, 4, 5, 6 are the losers. Now you're going to run this simulation. So for yourself, keep some tally marks. I want to see. Now here's what we're doing, right? You ready? Mrs. Gallus, her class, did this with 30 bottles of soda. What we're saying is, was that weird? Was it weird that they got 2? And so what we're going to measure that, is it weird? That was empirical, right? They bought the bottles of soda. We're going to measure the theoretical. If it's purely by chance, I have this perfect simulation of 6, right? Purely by chance, what are the odds that you only get 2 out of 30? So, roll and tally. Winners versus losers, 30 times.
So we roll those. The rest of the course.
This exact thing right here. Somebody says, oh, here's what it is. This is my claim. The probability of this happening is 1/6. And you wonder to yourself, I wonder if that's true. So you go out, you test it yourself, and you go, man, is my result weird? Is it just me? Or is it everybody else? So here's what we just did. Ready? Number of winners in 30 trials if 1 in 6 wins. You rolled the dice 30 times. The die roll simulated opening up a bottle of soda, right? So this represents exactly what they did. When those kids in this class did that, they got 2 wins out of 30, right? How many of our people got 2 wins? 2. So the question is it weird to get 2 wins? And really in the context of this, it means, did Pepsi rig this competition? Because if they got 2 out of 30 and we had a huge stack on 2, we'd go, oh, that's not weird. We got that by chance, right? So we're measuring what actually happened versus pure chance. So, are you kind of with me right now? On 5, there are 1, 2, 3, 4, 5, 6, 7. Yeah.
I don't understand what by chance to do with like how many they produce. Like it doesn't
Exactly.
affect how much they produce.
So it doesn't have really to do with the competition. But what we're saying is it likely that they just randomly grab these bottles and 2 out of 30 of them happen to be winners? Or does getting 2 indicate that there's a problem with this contest? Does that make sense?
So if there's a lot of 2s, like if there's a problem.
If there were a lot of 2s, we'd say, well, randomly, if there's a 1 in 6 chance of winning, because that's what the die represents. Randomly, if there's a 1 in 6 chance of winning, 2's not that uncommon to get 2 wins. Does that make sense? So there's a bunch of things going on here at one time. One is the actual contest, the empirical, right? So in theory, the contest is 1 in 6, but the empirical was we only got 2 winners out of 30. And so we think to ourselves, is that weird? So we design a purely chance scenario, the die. And we assigned one of them out of 6 by chance to be a winner. That's like me going to the cooler and going, okay, I'm grabbing this random bottle of soda. I crack it open, and by chance, I'm supposed to have 1 in 6. Well, we're measuring our empirical result of getting 2 versus what's the actual theory. And so by chance, we got 2 of 2 times. So here's what we're going to do. Because I'm down in number 7. What we're going to do is we're going to measure against an alpha level, meaning a statistical significance level. This is what we talked about last time. And so here's what we're going to do in number 7. We're going to put our number of dots on 2 over the total dots. And that's going to be a percent. And this is going to indicate the percent of times that we got 2 or less. Percent of dots on 2 or less. Put it over the total number of dots. And this is going to be the percent of times we got 2 or less. So let's count them. So there are 2 dots on 2 or less out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. What's my percent there? Say it again.
Three divided by 8. No, 2 divided by 12. No. Yeah, 1 divided by 12.
Divide on your calculator. What'd you get? Okay. So here's the question. Is it weird that we got 2 out of 30 of them? So you know the answer to this question, right? So, well, if it was below 5%, we'd say that it's weird. But the question that I want you to understand is like, why is that weird? Because what that would mean is this. Purely randomly. Randomly, I rolled this die. Randomly, a side came up. And 8.3% of the time, we got 2 dots or fewer. So, if the contest is purely 1 in 6 chance, 8.3% of the time, we got 2 dots or less. And the question we should ask in our mind is, so if I get 2 when I actually open the bottles of soda, is that unlikely? Does it cause alarm? Does it make me think that this contest is unfair? So what it means is, in theory, if we ran this contest 24 times with 24 different classes, which is essentially what we just did, right, without the bottles of soda, 8% of the time, the classes got 2 or less wins. Is that weird? Now, this is where the question comes in, right? Do you think 8% is weird?
A little, but not.
The problem is we don't get to decide in statistics. Right now, the only decision you get to make is versus 5%, is it weird? So here we go. If it is below or equal to 5%, it is statistically significant. I'm going to say this, and this is where the confusion comes in. So that would mean that it wasn't by chance. That would mean that it's rigged. If there was a 3% chance in all of my trials that people got 2 or less, and my class got 2 out of 30, there's only a 3% chance that it happens. And we got it, I would go, now wait, hold on a minute. Hold on a second. It's like the lottery. You have such a slim chance of winning, and someone wins, everybody's all over it. Where'd they get the ticket? Is it official? Did they actually win? It raises these big alarms because it's so unlikely to have it happen. That's this. It is so unlikely to have this happen, but it happened to us, so we go, huh, wait a minute. So what's the opposite? Above 5%. It is not statistically significant. Okay?
Because
Meaning it's by chance.
wait, so
Leon,
Back when I was 7, why did you do 2 or less?
2 or less, because is it more or less likely to get less wins?
it's also in the question. It's in the question.
That's 2 or it is 2 or fewer prizes.
Wait, okay. So for number 8, because it like, so like 5% is what, like the theoretical?
Yes.
Okay, and then 8.3 is what really happened. They're all like
8.3 is also the theoretical that we found from our simulation. So based on a theoretical model, our theoretical model of many trials, 720 trials, well, 24, so that's a third, right? We found that 8.3% of the time it was 2 or fewer. So then when I look at, because it's like 3 parts, it's hard because it's 3 parts, right? There's the probability of the contest, there's the probability that I find based on my trials, and then there's what actually happened that I'm kind of measuring. So what I said, if it was purely by chance, if the contest was truly random, I ran the simulation as if it was truly random. Because I'm trying to evaluate, is it really random? So I use a separate simulation to say, is it really random? Well, when it was really random, just a die, not soda cans, soda bottles, 8.3% of the time, there were 2 or fewer. So then I go, okay, let me actually do it. Open up. Okay, 2 or less, 8.3%, and then I'm thinking, okay, that's not really that weird. Because it actually, like when it was just purely random, 8.3% of the time it happened. And I'm okay with that because I'm setting my alpha level, the threshold at 5% right now.
that's confusing. And so the 5% is just like an always.
For now.
And then, so your actual answer would be, no, Pepsi isn't lying?
We have, no. We do not have convincing evidence that Pepsi is lying.
Okay.
So you'd say, we do not have convincing evidence that Pepsi is lying.
What would be convincing evidence that they were lying?
If we got
What you'd say is we have evidence to suggest that Pepsi may be lying, versus we do not have convincing
Yeah, but what would
evidence.
that evidence be? Like, it would be under 5%.
Sure. If our class had gotten 1,
Oh,
Out
it's
of
hard
30.
to get less than 5%.
yes,
Less
Yes.
than 5% of the time, you'll get a what?
a win.
2 out of 30.
2 or less.
Okay.
It's saying
So-
like it's very unlikely.
So I don't want to over-explain, like, it's just going to, it takes a while to understand it fully. But basically what happened is this. Pepsi said, here's our contest. It's 1 in 6. We did the contest, and we looked at it and we said, we didn't get 1 in 6. Is that weird? And so then we said, okay, if it was 1 in 6, it'd be purely random. So we used the die to say, if it was 1 in 6. So then we ran a bunch of trials, and we said, okay, if it was 1 in 6, and we did it 720 times, we got an average of how many wins? Well, then we said 2 out of the 24 times that we opened up 30 soda bottles, meaning we rolled the die, we got 2 or fewer wins. 8.3% of the time, purely by chance, we won this contest. So then we look at, well, then what does this mean for the actual contest that we did when we opened the soda bottles? So that would mean that our result falls at an 8.3% of the time, our result could happen. And what we've said is, if it doesn't happen less than 5% of the time, we're okay with it.
It's rigged. Yes.
If it happens less than 5%, if it just so if there's a 1% chance that you got 2 or fewer and we actually got it, we'd go, wait a minute, there could be a problem here. But because our result is not that weird compared to the theory, we're okay with it.
So on like a test or something, even if you got like, I don't know, 23 out of 24 times or something, like can they tell you your number is wrong? Like if it's by chance? Like there's not like if the number that you got was nowhere near 8.3, would it be wrong?
What if we had gotten 8 wins when we opened up? We might go, oh, that's weird.
Yeah, what if it's
Right.
too high?
It's too high. It doesn't matter. Because in theory, 8 is not that unlikely.
So you just grade by like if the word looks right?
Yeah.
By the number?
Okay?
Oh, it just, yeah.
How do we do this in the test?
On the test, you're going to measure, like you design an experiment.
But you don't have to actually carry it through.
Let's go to the next page. You're actually going to design an experiment. I'll show you kind of how it comes together. You're not going to get this. Ask Eric. We're going to spend the rest of the year trying to evaluate alpha level. Yeah. He gives it a thumbs up. Thumbs up means one of 2 things. I wasn't listening or I agree. I'll take both. The alpha level. All right. So let's talk about this for just a second. Simulation. Because what we just did was a simulation. A simulation is an imitation of chance behavior. It's where a model reflects a situation. Here are some examples. Flip a coin. Roll a die. A random number generator. Here's the process by which you use a simulation to model a situation. First, you need to describe how simulation models the situation. So in the case of the soda contest, we said, well, if there's a 1 in 6 chance of it winning, we assign one of the sides to be a win, the others to be losses. How could you use a random number generator to do the same thing? You can't pick 1 through 6.
What?
What's that?
Wouldn't you be like can you pick a question?
Saying how could you have used, instead of, for that 1 in 6 wins, how could you use a random number generator instead of a die?
7 parameters, 1 to 6.
Can't use 1 to 6.
1 to 720. 1 to
I mean, just do like 2.
It's how many
How
times
many
you roll the
choices?
die,
And
and
then
how many times you get a certain number. You choose a number that's a winning number, and then how many times you.
Set it 1 to 12, make 2 of the numbers winners. Right?
Why 2?
Why 2? Because it needs to be a 1/6 chance of winning.
Why can't you just do 1 to 6?
I'm just helping you think through the process of assigning a random number generator. So it could be 1 through 6.
Okay.
It could be 1 through 12. It could be 1 through 24. But to describe how the simulation models the situation, your proportion of winning needs to be easily incorporated into your model. Would you use a coin flip for this? No, because it's like a 50% chance of either event. So you wouldn't use a coin flip for this, where you could use a random number generator or rolling a die. So secondly, you need to record results many times. I think Vicky said this. Why didn't we just use a online simulator? You could. It works. I just wanted you to roll the die. And you use your results to answer the questions. So that's where you evaluate what happened versus what your simulation showed to determine is that outcome weird? Is it statistically significant? Okay. Let's talk about this, check your understanding. A basketball announcer suggests that a certain player is a streaky shooter. That is, the announcer believes that if the player makes a shot, the player is more likely to make the next shot. As evidence, the announcer points to a recent game where the player took 30 shots and had a streak of 10 shots in a row. This convincing evidence of streaky shooting by the player. Assume that this player makes 50% of the shots and the results of a shot don't depend on previous shots. So, the announcer is saying, I think it depends on it. We're saying, let's run a simulation that it does depend on it. Talk about a simulation at your tables that could model the situation. What we do in statistics is we evaluate a claim versus what if it's pure chance. The announcer is claiming this person is a streaky shooter. So what that would mean is that if they make a shot, then they're more likely to make the next shot. The alternative is that it's 50-50. They shoot, maybe it goes in, maybe it doesn't. And so what the announcer points out is what exactly we do. Hey, but they had a game where they hit 10 in a row. Okay, was that weird? Or could that just have been random? Could it just have been random and they just happened to hit it? Or is it true that when they do hit a shot, they are more likely to hit subsequent shots? Does that make sense?
So we're testing the validity of like the 50% probability?
We are testing whether this person is a streaky shooter by saying, is it significant that the person hit 10 in a row that one time? Because if you do this simulation, and there are some times when you hit 10 in a row, it's not significant. It could just happen if you're a 50% shooter. Yeah, Antonio could go out, he's a 50% shooter, and he could hit 10 in a row. Or, wow, that didn't happen really all that often. Holy cow. He must be a streaky shooter because it doesn't just happen. Leon.
Can't you just do it mathematically? Why do you have to use trials? Can't you just do like 50% to the 10th power?
The thing about doing 50% to the 10th power is this. That's maybe the probability that you hit 10 in a row, but it's out of a certain number, and so that's why we're doing this simulated trial.
Wait,
Does it
Okay.
matter how many trials you say? Because I put like record 425. You just need it. Is there like a recommended? Just many trials?
No, it's many trials for now. Does it matter how many? No, but you should have a good collection. To try to get to 20 or 30 is probably a good amount. Like our 24, that's pretty compelling evidence. 5 would not have been. So what they did was this. The dot plot displays the result of 50 simulated games in which the player took 30 shots. So what that means is they flipped the coin 30 times, 50 times. So 30 times, 50 times. longest streak in the simulated game. What does this one dot represent?
We got
One of the-
They
got
got
seven
seven
streaks in that
during
one game.
one period of
30
shots. During one.
That one dot above 7 means one streak of 7 in 30 shots of one simulated game. So make sure you understand that. Was that the only streak in that game?
No, but it was the
No, but it was the longest. So they may have had a streak of 5 or a streak of 2 in that game. What's that?
But they only have
I'm just saying, I'm just so you can understand this. Okay, so we can understand. So one of these dots is the longest streak in a simulated game. So what are the 2 dots above 9? What are those indicating?
9 is the longest streak in those 2 sets of 30 shots.
2 games with a longest streak of 9 shots made. So, now that we understand what we're dealing with here, do these dots represent players taking actual shots?
No.
No. This is the coin flip simulation. However they simulated this, this is what happened when it was purely chance. They could have done this with a die. 1, 2, and 3 are a miss. 4, 5, and 6 are a make. They roll the die. So 50-50. So when we see 1 dot above 10, that is a simulated player who shoots 50%, hitting a streak of 10 in a game. So what conclusion could we draw about whether this player is streaky?
No, just lucky. It was just chance.
No, he is streaky because he is streaky.
Yeah,
Because by
that's
chance,
like the top
it's
by
almost
chance.
impossible to kill.
Don't we have to do the math thing?
1 out of 50.
Let's do some math.
Can we do the math
So let's do the math thing. So what is the mathematical probability of by chance hitting 10 or more shots in a game in a row? So
Oh.
1 out of 50 times 10 shots in a row were hit by chance. Is equal, what's the percent on that? So 2% of the time, a 50% shooter just randomly hit 10 in a row. This dude goes and hits 10 in a row. No big deal. Or, whoa, that's weird.
But
It's weird.
but it's out of 30 shots, and this is only 10 shots.
No, it was out of 30.
No, 10 shots,
No,
shots in
because
a
it's
row.
below 5%.
Each dot, so there's 50 dots. That's 50 games where they did this 30 times. So this right here represents a time that they rolled the die, they flipped the coin 30 times, and there was a period of time, a stretch of 10 in there.
I'm talking about number 3. Like.
Yeah.
Wait. What? Oh, never mind.
So that's why this part is important here.
I misread.
Okay, that's why this part is important. So 1 out of 50 times, 10 shots in a row was hit by chance.
So
2% of the time. So what does that tell us about our player? Are they streaky
Yes.
or not? Yes. This is not likely to happen by chance. So this player must be streaky.
It's must be.
Yeah, they must be streaky. Because either they're streaky or it's random to happen. This doesn't happen very often randomly. So what we would say is, he must be streaky.
So it's this player, right? Like all of those simulations were like simulations of this player.
Yes, simulations of a player with 50% like this player.
A player or that player?
Well, there was just the,
No one shot these
it's
shots.
for that player to see if they
Yeah.
It's for
Oh, you're just comparing his like statistics. So
That's
his
right.
simulation.
Yes.
Okay.
Just-
And the fact that he did that seems okay. Because like if we were simulating like him doing it, do you know what I mean? And that happened, then wouldn't it feel like he wasn't streaky because he barely ever did that?
How do you simulate him doing it?
yeah, it's not. It's just
Without
you
him
can't see
actually
if it's
doing it.
statistically-
Okay, never mind. Yeah, I get it.
Okay.
Yeah.
I think so. I saw Gigi first, and then Lex.
So does this mean for like every simulation where someone, like how this one was saying, is this convincing evidence of streaky shooting? So if it's below 5%, does that mean they are what they claim?
If what they did is below 5% compared to what a model of pure chance simulates, then yes. Meaning, purely by chance, this doesn't happen that often, and they just happen to do it, whoa. That's crazy weird, because that doesn't happen that often.
It's like the predicting Parkinson's thing, isn't it?
Yes. Yes, exactly. It's exactly like the predicting Parkinson's things, because it's like, what's the likelihood that a person could guess that? Well, it's not that likely. Holy cow, she did it. Man, she must be good. Yes, that's true. Yes. It is when the result that you're measuring that actually happened is very unlikely, and you compare it to pure chance, and by chance it was unlikely, and they're even more unlikely than unlikely, that's pretty unlikely.
So what actually happened in this?
Which part? So he did hit 10 shots in a row. He actually did this in a game.
I thought that was a simulation.
Hold on. So he actually did this in a game, and the announcer goes, well, he's a streaky shooter. And somebody else goes,
Oh, I
well,
see.
that could happen. No, somebody could hit 10 in a row. Well, yeah, they could, but it's not likely. And so the fact that this guy did it says that, yeah, he must be a streaky shooter because it was unlikely that this would happen by chance. And the hard part is, it wasn't impossible that it happened by chance. It's just unlikely that it happened by chance. Yeah.
Then why do you say must be streaky? Why can't you say is highly likely to be streaky or
Because
like
he
is
is or he
most
isn't.
probably? Or
We don't split the hairs like that. We just evaluate the claim versus the probability.
Yeah.
So our only two alternatives in this, are either what he did was just a coincidence, or he's a streaky shooter.
Then why do we say for the Coca-Cola thing that they're like probably not?
Because we didn't have enough evidence to like make it.
We would just say we don't have. So let's say that he had hit 7 in a row, and it wasn't a 5% chance. We'd say we don't have convincing evidence about whether he's a streaky shooter or not, because it could have happened.
How do you know when we have convincing evidence and when we don't have?
5%. The 5% line.
Yeah, but isn't it, if it's below, then it's still like not completely impossible to just do it by chance.
We didn't reject the Coca-Cola thing, the Pepsi thing, right? But if we had gotten 1 lid, we would say this there's convincing evidence that this is rigged. It's rigged.
We would say it.
We have convincing evidence.
Okay, so it was too spread out to have.
Right.
Okay.
Leon.
What would happen if you get 0 tries on 10? Like 0 times it happened on 10? In the 50 simulating.
It's even more likely that he's a streaky.
Yeah, but
Yeah.
so what would the probability be? 0?
Yeah, you just put it in the math.
No,
Yeah,
because
so-
this is a simulation.
Yes. So this is a simulation, and so what you do is you'd say 0 times out of that it was. So he must be a streaky
So
shooter.
it's
Because
clearly
0 is less
possible
than
because
5.
he didn't.
Yes, 5 or less. It's 5. It's 5 or less percent.